Okay, hello everybody. Welcome back to the second video of the series. Today we're going to be talking about Transformers, and hopefully this video will be a lot shorter than last time. Okay, so what Transformers are is basically stuff like ChatGPT or whatever that generates new text. The Transformer is a way to train a model to use sequential data um, to improve its predictions, basically. So this is what the outline of a transformer is. I'll just give it like this is just the overview. You have words, they turn into tokens, you embed the tokens, you encode positional information, you put it through this block here, and then you have multiple blocks however you want, and then you transfer this into a probability distribution over all the vocab that you have. And then it just goes. It's called auto-regressive because it just uses the information, its previous information, and then adds on the next prediction and then just does it again. Okay, so to start off, we'll talk about tokenization. So we have a data set here. Um, this is just a sample from it. And what tokenization does, it's turning these words basically just into numbers, and it doesn't use each word as a single number. It basically chunks it up. So you might have super long rare words. You don't want this in um the output as a in the distribution because it might only be seen very rarely, and so it would get like a zero probability. And this would also, having the vocab size, the size of the English language would be like multiple 100,000 vocab size, which just makes it computationally more expensive. So what you do is you chunk up the words. Also, basically, you start with characters and you join characters together that are seen like most frequently, and then you join those join characters together, and so you just get so you have 26 letters, and the 27th letter is maybe two L's that get combined into the token 27, which is two L's, and they just get combined. So here, this is our vocab has 12,000, I think, 14,000. This is from our data set. The original tokenizer I'm using from the Meta model is 140, 130,000, but because this is trained on so much information, it has stuff that is not in our data set that we don't really care about, like this, like all this stuff, dot background, so like coding and whatever. So this example of what the tokenized data looks like. So you have the 44,000 token. Yeah, and this is this little string here. Yep. And so this is mapping um our tokens. It's mapping the Meta's tokens to our tokens, so it just reduces the vocab to what our data set has. And then you split the data up into train and test, train and validation. So you don't want to check how well you're doing when you're training on the data you're inputting it because it could just be remembering everything. So you give it some new data to check how well it's actually doing. And we better go with this. So this is once you have the tokenized data, you have a number. So this might be um the chunk of letters LLE, I guess. Um and so you have token embeddings. You basically give it the however many dimensions you want the information to be um displayed in. So you could give it like 100 dimensions to represent its information. Um, and these get trained on just a massive amount of data to sort of become more similar to words that are semantically similar to it. So the words like ocean and wave would have more similar vector. This is like a n-dimensional vector, how big your embedding size is. And so in like that dimensional space, the sort of vectors point closer together if they have similar meanings. And so you have positional embeddings, which is basically you just add on some positional information to the token embeddings, I can say. It's not that complicated. Well, it is complicated, but it's not that interesting. And so now this vector sort of has an information component about what the token means because it's already been trained, this token embedding. And it has incorporated the positional information. So where this token is in the context length. So you have like a sliding window, which is the context length, which is all the information the model is looking at to get to the output. And so you have the first one and you have the last, which is the size of the context length. Okay, so this is what you have the token embedding, which would give so you have the vocab size is 14,000 whatever, and say you only want to give it 5 dimensions. So it gets this many numbers to represent its information. And you do that for all the tokens that you have. And so these are already these are trained to have semantic information, and then you add the positions onto it. Okay, so then we get onto the attention mechanism. So we have here, we go into the transformer block, and then you normalize, put it through a linear layer. That's not that important, but this is the main part of it all. So, well, let's explain how you create training examples. So you have your data. You want to how you need to train it is you have a series of tokens, and then you want to predict the next token. So you pick a random chunk in your context size. So say your context is 500, you get 500 tokens for a training example. But in each of those 500 tokens, you can say a training example is the first token looking at the second token to predict the second token, the first 2 tokens to predict the third token. So you have all of those examples up to 500 different training examples, you could say, because they have different contexts. And so you pick a random point in your data set, and then you take that information from that point plus the context length that you want to have. So the block size is called. And then, so that is one sample. And then you get the next tokens for all those tokens in a separate target tensor, which is basically the same length, but for all those tokens, it's just the next token. So say in the first line, you say this, where are some tokens? Up here. So this is example. This is a training example, you'd say. This is the first token. In the target tensor, you would have this one as the first token because this is it's basically the predictions or the answers tensor, and you have it for all your token length. So you have the same size, but it's just the next token. And then you also want to make multiple samples in the one sort of tensor object to utilize your GPU better because it's better at doing like parallel computation. Okay, so once you have that, you have a batch dimension, which is the number of examples that goes down. The block size dimension, which is the size of the context, which is lengthways, and then you have the embedding dimension because each of those tokens, it's 3D, goes that way of the positional and token information, this stuff. So it's a 3D tensor. And so what you do is you get a linear layer that goes from the embedding size to 3 times the embedding size. So what that looks like is here. So you have this is a single example, booked. This is the embeddings down this way. And you just basically feed it through up here to get 3 times the embedding dimension to give you what's called queries, keys, and values. Um, yep, so that's it here. That just splits up this. This is the linear layer, and then it splits it in the second dimension, 1, 2, which is the embedding. So you get 3 basically identical vectors at this point. And then this is just some reshaping to work with multiple heads, but that doesn't make any sense right now. But what you do basically is you have the queries, keys, and values matrices are learnable transformations of the embedding information. Because these are neural nets, basically, you can adjust the weights to have a different transformation of this X data. So this will give a different interpretation here, here, and here. And what is good to think about this is the queries matrix is basically the attention is sort of communication between tokens saying what information is relevant in my context, what other tokens are relevant to me in predicting the output token. So you have the queries is basically asking what information am I looking for in the other tokens. The keys is what information do I have, and the value is that's for later to sort of scale the tokens. It doesn't actually mean this, but that's just how you can interpret it. What it actually means, it doesn't mean anything. It's just an interpretation of this embedding dimension that you can adjust to represent information, basically. That it learns to adjust based on its prediction error. Okay, so you compare the queries and the keys for all the tokens with all the other tokens. So bring this over. So you have if you have a 4 token string, say that's your context size, you take the query and you dot product it with the key for all the tokens. And the dot product is basically the similarity between the embedding dimension. So it gives you high values for similar vectors and low values for like dissimilar. And so what we have, so you get a matrix of comparisons between all the tokens and all the keys. And what's happening here is um, because you want it to predict the next word, you don't want it to be able to look at say for the first token predicting the second token, you don't want it to be able to look at the third and fourth tokens. And so for that training example, you only have it predicting off this first one. And so these all set to 0 when we get down here. Well, maybe this is a better way to explain it. So you have this creates a lower triangular matrix, lower triangular ones matrix, which is down here. So you can see that the bottom triangle is just ones. And then this, okay, step back a little bit. This is the dot product. So this is the similarity between the queries and the keys, and this is just scaling to make it train better. And so you get an output of the similarity between all the tokens. Then you dot product with this matrix down here, which is where you multiply it, I'd say. So it turns into this, and softmaxing 0 is turn it to negative infinity, Well, no, it starts off -3, softmaxing turns it to 0, I believe. Well, this just turns it to infinite, -infinity, sorry. So when you softmax it, the probability sum to 1. So for each row, which this has been scaled already, but this one here, yeah. So this is 1. This row sums to 1. These sum to 1. And this is basically the attention scores that a token attributes to the other tokens, you can say. So in predicting this last token, this token has a better way. This is just random, but you can see how the different tokens have different values. I'm not sure if I explained that correctly, but you basically get a comparison score for all the tokens. And then you multiply this with the value matrix, which is just taken from the original X embeddings, and it's transformed in a particular way that's learnable into the values. So this is just an interpretation of the original X embeddings, and then you scale it by the attention scores, by how important each token is. And so that is communication. So it's sort of shifting around information based on which tokens are more important. And then you have to put it through a multi-layer perceptron layer to actually learn the information, to learn the prediction. So that's what's going on here. You have just a linear turns it into the hidden layers 4 times the embedding size, non-linearity, and then back down to the embedding size. Okay, so that's done that. This layer norm is basically just normalization for better training. Feed forward is the multi-layer perceptron, which does the learning. And then this just feeds through multiple times. And then we're going to normalize again a linear layer, which transforms from the embedding size down to the vocab size. So you get a sort of a distribution over all the tokens you want to predict. And this gives you like scores for what it thinks each of the tokens will be. And then you just softmax it over that so they all sum to 1. So it's a probability. Yeah, and then you can train that. So it'll generate a prediction based on what it thinks is the most likely. And then you use cross-entropy loss, which is basically when you have categories, you use this to compare how well the prediction was based on the targets, which is the targets is the same shape as this, but it's just the next token. So you can see what token it predicted versus what that true value was. Okay. Whoops. I don't know how to get that back. View, gallery view. Anyway, so this is basically what we were doing before, but the the trick is the query keys and values basically is one head is what's called. And so it's one interpretation of the embedding. And if you have multiple heads, you can learn different sort of information about the input. And so each head has its a unique interpretation of queries, keys, and values matrices that it transforms the embedding from. Um, and so yeah, so you divide the embedding into it squeezes it down into a smaller interpretation, and you do this multiple times for each head, and then you just combine these together at the end. So it combines information from multiple interpretations, is basically how I understand it. And then we go to train. This is just like the gradient descent. So you get the batch by time by embedding dimension, which is the batches down that way, time, and then the embeddings go like 3D that way. And then the targets is just the correct token. So this is a training batch. Send this to the GPU. The logits is just the, where are we? Yeah, this is the output of the model, what it thinks the its prediction is, and the loss is the cross entropy loss, comparing it with the target, which is the true value. So you've got a measure of how well you're doing, and then back in the previous video, we talked about what gradient descent was. You find the gradients of the weights with respect to the loss. So this is um all the weights are all the different transformations and the queries, keys, and value matrices and the multi-layer perceptron layers, all those weights. So you can adjust them all. Um, yeah, and then you use the optimizer to adjust them basically to get better predictions. And then you can and then you basically have to decode because this is using tokens. You decode the tokens back into um text basically, which is like chunks of text. So you see, because these is not complete words, it combines chunks like alone is probably one and Odiac is one. It combines them into words that don't exist. And this was, I think this is different. I think this is, yeah, I think this is Shakespeare. Yeah. So this was trained on like a Shakespeare data set, which is like from this guy, Andrei Karpathy. He's the goat. And so after training a lot, you get some like half decent examples, and so your loss is down to 0.055. But remember, this is trained evaluated on the training data, so it's you wouldn't use this really. And yeah, this is example. So it's learnt like the you start a passage with the person's name, and it sort of makes sense. Of my lord's tricks and yours when you were boys, you were pretty lord. So it's pretty good. Um, but yeah, and that is how it works. Is it's all it is a document completion, so it's just predicting the next word. And to get something like ChatGPT, you need to fine tune it to basically convince it it's a question answering bot that is just completing documents with questions, and it gives the answer. So it is just filling out documents where you give it the Q is your input and it's just filling out the answer, which is the format it thinks it needs to do. But yeah, I hope that was somewhat useful. I hope you guys learned something, and I hope I learned something as well. Okay.